Alright, so this is a very important article, Fast Model Editing at Scale. This article in 2022 in ICLR. While large pre-trained models have enabled impressive results on a variety of downstream tasks, the largest existing models still make errors, and even accurate predictions may become outdated over time. Because detecting all such failures at training time is impossible, enabling both developers and end users of such models to correct inaccurate outputs while leaving the models otherwise intact is desirable. However, the distributed black box nature of representations learned by the large neural networks makes producing such targeted edits difficult. If presented with only a single problematic input and new desired output, fine-tuning approaches tend to overfit. Other editing algorithms are either computationally infeasible or simply ineffective when applied to very large models. To enable easy post hoc editing at scale, we propose this MEND, Model Editor Network with Gradient Decomposition, a collection of small auxiliary editing networks that use a single desired input-output pair to make fast local edits to a pre-trained model's behavior. MEND learns to transform the gradient obtained by standard fine-tuning using a low-rank decomposition of the gradient to make the parameterization of this transformation tractable. And it can be trained on a single GPU in less than a day, even for 10 billion parameter models. Once trained, MEND enables rapid application of new edits to the pre-trained model. So you see the proposed algorithm that enables editability by maintaining a collection of MLPs to modify model gradients to produce single model edits that do not damage model performance on unrelated inputs. So there are three important measures for your own model editing: reliability, locality, and generality. Our approach trains lightweight model editor networks to produce edits to a pre-trained model's weight when provided with standard fine-tuning gradients of a given correction input, leveraging the gradient as an information-rich starting point for editing. Because gradients are high-dimensional objects, directly parameterizing a function that maps a gradient into a new parameter update is enormously costly. Even for a single DeepID weight matrix, a naive implementation requires a mapping which is impractical for large models. So by decomposing this gradient into rank 1 outer product form, our approach is instead able to learn a function G. So you see the MEND architecture consisting of two consecutive blocks, both initialized to compute the exact identity function. On the left, the input to MEND network is delta and U, the components of rank 1 gradient. And on the right, a MEND network produces a new rank 1 update, which is added to the weight to edit the model. The goal is to enable the use of a single pair of input and desired output to alter a base model's output, as well as its equivalence neighborhood. The base model is a differentiable function that maps an input and a set of parameters to an output. A model editor is a function E that maps an edit input, edit label, loss function, based model parameters, and optional editor parameters phi to a new set of model parameter theta E. So we call a model editor reliable if the post-edit model predicts the edit label y sub e for the input edit input x sub e. We call a model editor local if the disagreement between the pre and post-edit models on unrelated samples. For example, if the expectation of KL divergence between them is small. Finally, we say a model editor generalizes if the post-edit model predicts the label when conditioned on x prime of E. We call a model editor efficient if the time and memory requirements for computing phi and evaluating E are small. We define edit success to summarize both reliability and generality. So with the parameterization, MEND learns G sub L with parameterized phi sub L, which maps U sub L to delta, to pseudo-activation and pseudo-delta. The model edit for weight matrix is this. To further reduce the number of additional parameters, MEND shares parameter across editor network G sub L. Because the sizes of U sub L and delta sub L plus 1 depend on the shape of the weight matrix, MEND learns the separate set of editor parameters for each unique shape of weight matrix to be edited. Editing all MLP layers in a transformer-based architecture, this sharing scheme entails learning only two sets of editor parameters, corresponding to the first and second layer of each MLP. To enable some layer-wise specialization, MEND applies a layer-specific scale and offset to the editor network hidden state and output. So MEND parameterized G sub L as a MLP with low-rank weight matrices, residual connections, and a single hidden layer. And for locality loss, we have KL divergence between their predictions.